Okay, hello. So for the third video, what we are going to do is we are going to explore the ideas in special relativity. So why special relativity is important? Because in 1905, Albert Einstein recognized that the Galilean principle of relativity needs to be modified. And why is that? Let us explain. So basically, at that time, there was a huge gap created in physics because Maxwell theoretically proved that there is a speed of there is a particular speed of, let's say, Maxwell speed of electromagnetic wave which travels at c. So when Maxwell derived these electromagnetic field equations, and he got the he got a constant speed, and that it was not clear at that time, like what was the frame of reference there, because speed depends on the frame of reference, like two particular observers which are moving with respect to each other, they are not in general thought to be thought to observe the same speed of something, right? So there was a huge controversy or huge gap in physics, and then at that time, the only solution, there were many solutions, but the most accepted solution at that time was to consider that the speed of light was with respect to a hypothetical medium called ether. So there is a ether which is filled, like there is a earth, and then it is filled all around the universe. And the speed of light, or rather the speed of electromagnetic, let us call it that. The speed of light c, it was found to be constant. It was measured with respect to the ether. So if you are here on Earth, and since the Earth is moving with respect to the ether, so this means that on Earth at different seasons or at different points in the orbit around the sun, the Earth should, on the observer on Earth should measure the different speed of light. So that was the theory at that time. But then Michelson and Morley, they conducted this painstaking experiments of for years to at different points on the Earth in order to measure a little bit difference of the speed of light based on their interferometer, but their result was zero. It was negligible. So negative results were there. Negative here means they did not detected any difference in the speed of light. They always measured the same speed of light. What does this mean? This means that there is a constant speed of light which Maxwell predicted is through his theory of electromagnetism. Constant speed of light with respect to every inertial observer. Sorry, this spelling is wrong. Inertial observer. This was the conclusion of the negative results of Michelson and Morley. So the thing here is, if you want to read more about Michelson, Morley, and the alternate theories to explain these results, you can read books like Kleppner and Kolenkov, or even Feynman lectures on physics. They give good details of the alternative theories, but I'm not going to discuss that here. So the ultimate idea I'm going to conclude here is that the Einstein concluded that with respect to every inertial frame, there is a constant speed of light. So, for example, if, let's say, there is a train which is moving, and Einstein loved trains. He thought of many, thought experiments with respect to trains. So if there is a train moving with respect, with velocity v, with respect to whom? With respect to a person here on ground, and there is a person inside the train as well. And if, let's say, that I turn on the laser beam, this is, let's say, my laser, and it goes with some velocity c. So this c is with respect to this, let's say this frame is s and this frame is s prime. So this c velocity of light with respect to is s is also c, and the velocity of the light, L is for light, with respect to S prime is also C. This is the first axiom of the relativity. That's where the relativity starts. This is the first axiom. And the second axiom is that with respect to all inertial frames, the laws of physics, and by laws of physics, it is a loose term, but rather what we mean here is that the equation of motion, they do not change their forms in different, even if you change the inertial frames, the equation of motion don't change their forms. That's what is meant by the laws of physics here. So with respect to all inertial frames, the laws of physics are same. This is the second axiom of the relativity. So this is the new relativity principle, and we will not call it new, rather we'll just address this one as the relativity principle. The older one was where the light, the velocity of different particles measures was Galilean principle of relativity. Okay, so an immediate conclusion to the relativity principle is that let us consider a thought experiment. This is original thought experiment conducted by Einstein. So the thought experiment is very simple. Let me just explain. Let's say this is a huge train, okay, and you have to imagine very fast speeds. If you don't imagine fast speeds, then it will be difficult to visualize. So imagine the fastest train that you can ever imagine. Okay, this is a long train. Now there is an observer here, which is S. This is S prime, let's say, and it is obviously moving with respect to velocity, I mean, with velocity v. Okay, so the thought experiment is, let us say that two lightning bolts strike this train at the rear and the front end. So let's say this is my rear end R and this is my front end F. Okay, now what we are saying is with respect to S. So here we are making lines, dividing it in tabular form so that we can clearly see with respect to which frame we are talking, because that is very important in special relativity, and we'll see why. So with respect to S, I am asserting, assertion is that lightning bolts, lightning bolts are simultaneous at R and F. So there is basically there are two events. One event is one lightning bolt from here. Let's say one lightning bolt from here and another lightning bolt from here. So there are two events striking. Let's say this is lightning bolt. I'm very bad at drawing. Please bear with me. So the time event between these two events is simply zero, because they are simultaneous with respect to S. Now let us see what is happening with respect to S prime. Now imagine that I have an observer in exactly the middle position of the length at the length of the train, and let us see what is going to happen. So one thing we know before, I mean the umbrella of the assumption is that the speed of light is constant. Okay, so let's say that at a given instant this lightning bolt strikes here and this lightning bolt strikes here with respect to S. Okay, now this lightning bolt, the light will travel from this bolt, the light will travel here from front, and then from rear it will go in this direction, right? Okay, now with respect to S prime, because the observer itself is moving towards the front lightning bolt, so because let's write, because the observer O prime is moving towards front end lightning bolt and away from the rear end rear end bolt. Okay, so this is one observation. The another observation is that, and the speed of propagation of light is same. So it is same, both emerging from front and rear end. So that's why front and rear end. That's why we conclude that what these two events will not be simultaneous with respect to the prime frame, which is our S prime frame. So delta t prime is not equal to 0. Okay, which one will arrive earlier? The front end bolt will arrive earlier. So we can also say that t at f is greater than, sorry, my bad, because it arrive earlier, its time will be less. So t of the rear end is greater than the t of f, which means that delta t prime is not equal to delta t. So what do we conclude here? I mean, you can do this analysis with completely rigorous mathematics. Just put in the constant speed of light, measure the distances from, let's say, you have fixed one origin, and then you do this analysis, and then you will get the same results. So this is intuitively clear here, but obviously you can do that mathematical analysis. It is not so difficult. You can do that on your own. It would be a fun exercise to do as well. Okay, so delta t prime is not equal to delta t, which means that simultaneity is relative. Simultaneity is something which is relative. Simultaneity is relative. Okay, so which means that there should be some transformation laws that should exist from S prime to S. Okay. So let's say if I know the events, the interval of events which is happening in S prime, then I should be able to at least relate it to the what is happening with respect to the S, right? So this is called coordinate transformation laws. So originally in non-relativistic mechanics, they were there were Galilean transformation laws, which are very simple. I can write them. So let's say if this there is this S frame and then there is this S prime frame which is moving with V, we can obviously write them in general 3D, but just let us stick to 1D because it is easy to see there. So let's say that this is X prime, Y prime, and Z prime. Okay, so what we can do is we can simply write x prime is equal to x, where this distance here from here, this distance is x and this distance is x prime. So we can see that x prime is basically x minus vt, imagining that at t is equals to 0, this origin O prime and O coincides. So x prime is equal to x, y prime is equals to y, z prime is equals to z, and most importantly t prime is equals to t. This was the original non-relativistic mechanics Galilean transformations. But as I've explained to you right now, delta t prime is not equal to delta c. So we have to abolish these Galilean transformation laws and we have to find new transformation laws based on the assumption of constant speed of light. I will not again do this derivation because if I do every derivation, that will be very difficult to be on the path of classical field theory. So I will simply write the results, and the results are called Lorentz transformations. You can look up the derivation of Lorentz transformation in books, many books. Mainly, if you want to see, you can see in Robert Resnick's Special Relativity. Classic derivation is there. You can see that. I'm just going to write the results. The results are that x prime here is gamma x minus vt. Okay, and t prime is gamma minus Vx by c square plus t, and y prime is equal to y and z prime is equal to z, and that is because uh, the motion is in the x direction, so the directions perpendicular to the direction of motion of my frame of reference S prime, they are not changed. By the way, I think I don't have to even look at Robert Resnick derivation. I have a video on 3D Lorentz transformation, which you can see in one of my playlists. In 4D playlist is there, named by vectors and general relativity. There you can see the 3D Lorentz transformation and the ideas behind it. So I'm just writing the 1D version of it. Okay. So these are the Lorentz transformation where this gamma here is, this is for Lorentz scale factor 1 minus v square by c square. Okay, so my final, before ending this video, my final conclusion is that we can obviously write these forms, these in differential forms as well for two very close events. But the most striking result of the Lorentz transformation is that a very strange type of a quantity like this one is invariant. So this quantity is invariant. What do I mean by invariant? It simply means that this is equal to the dt prime square minus x prime square plus y prime square plus z prime square. Isn't that amazing? It is very striking result that even if, let's say, you have, I'm again, just imagine this train which we were assuming in thought experiment, okay, and this lightning bolt striking. So this is my s prime frame, this is my s frame, this frame is moving. So there is a s prime frame, the lightning bolts are there, some two events are happening, okay, and then those two events are separated by a particular time dt here, right, and the location of that event, spatial location, is given by x, y, and z. Similarly, if you observe the same interval of events, or rather here it should be dx, dy, and dz, my bad, and d and t, because we are talking about differential, very tiny, very closely uh, spaced events in space and time, basically. So this quantity c square dt square minus this spatial distance square, change in distance square, is invariant. So even if you measure this in s frame or s prime frame, it doesn't change. And why only s prime? Imagine if there is another frame which is moving, s double prime frame, which is moving with some, let's say, velocity v1. Okay, again this should be with respect to, of course, the s frame here. Okay, so of course this quantity is still is same. So I find this results to be very amazing, and this is a straightly, this derives from the transformation laws, which in terms is derived from the requirement of the constant speed of light. So here we see that the space and time are combined in certain manner so that something is uh, invariant. Okay, so to give you the intuition, really, why we can treat the time as a coordinate. So there is a big motivation here. If you look closely, there is a big motivation here why we should treat time as a coordinate. The simple reason is that, let's say, assume that we, in general non-relativistic mechanics, I'm just going to give a simple example. So if we have this x and y, and if we just rotate this x and y, make x prime and y prime, let's say we have some rotation. If I ask you this question, what is something which is constant even after rotation, the coordinates themselves change? So let's say we have a point here, we have a point here, okay, these x and y lengths, they are changed. So we clearly say that x prime is not equal to x and y prime is not equal to y. So obviously prime coordinates are not the same as the original coordinate, but there is still something which is invariant. So the distance between, from origin to this point, and from origin to this point is same, P point, P point, O point, O point. And why only distance between O and P? Any two particular points, P prime, P double prime, right? This distance or distances between points is invariant under rotation, right? So this is something we know, like that the distances are constant. Here, if we look closely, this is not a distance in a particular sense. There is this weird minus sign in spatial, and then there is a time coordinate. But this is how the geometry here is. So it is basically indicating that this is a type of non-Euclidean geometry. This is not a geometry very familiar to us. Rather, this is hinting towards a non-Euclidean geometry, a different type of geometry existing when you consider the time as a coordinate. So if you consider time as a coordinate, this c dt square minus dx square plus dy square plus dz square, you can call it as something called ds square. So you can obviously call it as ds square, and I will just write it as dr square. So this ds square you can call is space-time distance, not the space distance. It is a space-time. So space and time are clubbed here together, and then this is how you define the distance. And why this is a distance, why we are calling it a space-time distance? This is from the above analogy that the distances in prime frame are invariant. So we found this particular quantity, mathematical quantity, to be invariant. We are calling it as space-time distance. Okay, so I think it is now complete the idea. I hope the ideas of relativity are very much clear to you by now. So we'll use these ideas. We'll use this space-time distance to further explore what our Lagrangian could be, and I will point out to the facts, or rather, I will just point out why our Lagrangian in special relativity has to be changed. So we know that our Lagrangian in non-relativistic, let's say L of non-relativistic, we know that it should be T minus U. Then what should be the Lagrangian of relativity, relativistic? And the thing is that the limit when, let's say, V by C is rather V by C goes to 0, in that limit the relativistic Lagrangian should tend towards the non-relativistic Lagrangian. So our relativistic Lagrangian should pass this test. This is very important, right? Because if velocities are much less than the speed of light, right? So in that case, our non-relativistic Lagrangian should be valid. This you might know already that uh, under this particular limit, every relativistic result should tend to, and this is not with respect to Lagrangian only, every relativistic results under this limit should tend to the non-relativistic result. That is the test of, that would be the test of whatever we derive in the relativity theory from now on using Lagrangian, relativistic Lagrangian. Okay.